Okay, so I'm going to do this one a little bit different. I'm going to start off with this page. I'm going to show you some of the key equations. Then I'm going to switch over to the paper, and I'm going to solve this problem. And the problem is, what's the magnetic field due to a long straight wire? And I'm actually going to do this two ways. So the first way is to use the law of Biot-Savart and calculus. And that's the way most textbooks do it. The second way is to take an actual wire and break it into a finite number of pieces and then manually calculate the magnetic field, the vector magnetic field, and I'm going to use Python for that. So I think I'm going to have a good time. I don't know how long this is going to take, but I'm going to do it as long as it takes. I can do this all day. That's what Captain America says. Okay, so on this page, let me just point out some of the key things. Let's see the mouse. So this is the law of Biot-Savart. This says if you have a moving charge, it makes a magnetic field. And then the next thing says that down here, if I replace that moving charge with a little piece of current, with a current I and a length dl, then that is the same as a moving charge qv. But in both those cases, if I want to find the magnetic field at some location represented by this red dot, then I have the vector I dl, and then I have the vector r, which is from that location of the charge, the current, to the observation location. And those are my two important vectors. So then I have this I dl cross r hat. Now you can actually write this as I dl cross r, and then divide by r cubed. But I think most textbooks like it this way because you have a 1 over r squared term in there, and that's very similar to the Coulomb field for the electric field. So like, hey, it's kind of the same thing. But r hat is a unit vector. It's a vector that has a length of 1 and no units pointing in the same direction as r. And then so that's important because you can't take the cross product with a scalar. So in order to have a cross product, you have to have another vector. And then r is the magnitude of that distance, and then you square that. And then this mu naught over 4 pi is just a constant. It's the Coulomb constant, 10 to the negative 7th Tesla meters squared per Coulomb meters per second. That's the easiest way to write it because then all the units seem to work out. But that's what that is. And so what I'm going to show, the first part, is this equation right here. I want to derive this equation. The magnetic field due to a wire is mu naught over 4 pi times the length of the wire times I, the current, divided by the square root of r times the square root of r squared plus L over 2 quantity squared. And so that r is the distance. I'll draw that a picture. That's the distance from a perpendicular distance from the wire, right? Because you're in the, if it's a long straight wire, then you're essentially in the, you'd be in the middle of that wire. So that's where we're going to do it. And then we're going to take the case that we're close to the wire or the wire is very long, and then we get this other expression, which we can also derive with Ampere's law, but I'll do that in another video. So today I'm going to derive that right here. I'm pointing at it and you can't even see it. This magnetic field due to wire, and then I'm going to do it numerically in Python. Let's get to it. I'm kind of excited. You know, and I'll let you know I might make a mistake, and I'm okay with that. Okay, so let's switch over here to paper. There we go. Okay. So I had to move my camera, so things are a little bit out of line. So let's say that I have my wire right here. And I want to find the magnetic field right here. Okay, so now I'm actually going to call this, let's put this on the origin. So let's call this the x-axis. Let's call this the y-axis. And then this is a length L with the current I going up. And I'm going to go ahead and pick some values here. I guess I should. So let's say I is 1 amp. And then L is, I'm just picturing in my mind, a length of a wire. I could say 1 meter, but that seems like it'd be boring. So let's say 0.5 meters. And then I can find a value for x for later, but let's just say x is 5 centimeters. So this is my x value right here, the distance from the wire in the middle to the point where I want to find the magnetic field. And I'll say x equals 0.0, what did I say? I said 5 centimeters, right? Okay, so 0.05 meters. Okay, so now what I want to do is to pick a piece of the wire. I can't just do this all in one section, right? Because each part of the wire has a different distance and a different direction to this point right here. So what I need to do is pick a generic piece. So let's say here's my little piece of wire. I'm going to call that actually dy, right? Because it's in the y direction. And the current is going up. So if that's the case, I'll draw it in red. This is my vector r. I wanted to make it straight. That's the vector r. And I do need that. So I need the vector r and the I dl like that. Okay. So let's write down the magnetic field due to that little piece. dB, right? It's not the whole magnetic field, just the magnetic field due to that piece. It's going to be mu naught over 4 pi, which is a constant. I guess I should write it as dl for right now. dl cross, I'm going to write this as r over the magnitude of r cubed. And I'm going to do that because that way I don't have to find that unit vector. If you did want to do that, you could say r hat is r over r. Okay. So this is the cross product. So if I have the cross product, I'm just going to do this the long way. Let's write dl and r as a vector. So this is actually the location, the distance y up the thing, and that's a value x over. So I can say my observation location, I'll call that RO, is going to be the vector x, 0, 0. And then my piece up here, which I'll call r wire, is going to be equal to 0, y, 0. So that means I can find the vector r. The vector r is going to be from here to there. So it's going to be this minus that. So it's going to be x minus 0, 0 minus y, I get minus y, 0 minus 0. That's this vector right here. And it changes as I move up and down the wire. So I'm leaving it generically. My x distance, I'm saying, is that constant value. Okay, now what about dl? dl is going to be the vector 0, dy, 0, right? It's a vector in the direction, in the y direction, so that's that. Now I can go ahead and do this dl cross r. So let's do that. So dl cross r, I'm going to use the determinate version of the cross product. So I'm going to say x hat, y hat, z hat. Now I'm going to put the x components of dl, which is going to be, the components 0, dy, 0, and then r is going to be x, negative y, 0. Now I take the determinant of that, I get x hat, my first component, it's going to be dy times 0 minus 0 times negative y, which is 0. Then I get this term, I'm expanding about this row. This term, it's a negative, right? So I actually have 0 times x, which is 0, minus 0 times 0, so it's 0. And then I have the z term, it's going to be 0 times negative y, gone. But I do get this term, minus dx, x dy. So the only component I have that's not 0 is in the z direction. And this says it would be into the paper. So if that's my x-axis, that's my y-axis, which I cut off a little bit. Then z, the magnetic field, would be into the paper, which is in the negative z direction, and that agrees with that. And it doesn't matter what my value of y is, right? Because dy is always the same. So all of my magnetic fields are in the z direction. That's really nice. That's nice because it's going to make things a lot easier. Okay, so there's my, this is that part up there. And it's only in the z direction. So now let's just write the z component of the magnetic field. So I'm going to say dB, I guess I should redraw my picture. I'll save this paper for scrap later. Okay, so I'm going to draw my picture because that's going to be useful. There's my wire. This is my location. That's x. That's dy. And that's r. Okay, that's where we were. Okay, so I can say dB z is mu naught over 4 pi. This is the z component. So now when I take I, and then I take dl cross r, I get negative x dy. I already did that cross product. That's what I get. And it's a scalar value because I'm only in the z direction. And then I can divide that by r cubed. And that's the x value right there. So that's just the magnetic field due to just that piece. So in order to get all the pieces, I have to add up the contributions to all these pieces. This is really important because we're going to be doing essentially the same thing in Python. This is distracting. Okay, so what I want to do is add up the pieces from down here to there. So this is at negative L over 2, and this is at L over 2. So I'm going to say BZ is going to be the integral from negative L over 2 to L over 2 negative mu naught over 4 pi I x dy over r cubed. Okay, so I can't integrate because x is a constant. I can bring x doesn't change for this particular integration. As I move these pieces up and down, x is still the same. So that's a constant. Mu naught over 4 pi is a constant. I is a constant. But r is not. R changes. This is y, and that's x. Then I can write r is equal to the square root of x squared plus y squared, because this is now a right triangle. So the base down here is x, the height over here is y, the hypotenuse would be this x squared plus y squared is r squared, so r would be that. So I can put that in up here. I'm going to rewrite this as, I'm going to pull this stuff out. So I have I x mu naught over 4 pi, the integral, I'll leave off the limits right now. I have dy over this cubed. So that's going to be x squared plus y squared to the 1/2 raised to the 3rd power, so to the 3/2. Now I can integrate this, right? Because I have the integration variable dy. The only thing in here that changes is y, so it's an integral. How do you integrate this? I honestly don't remember. It probably is using parts, but I'm not going to do it. Instead, and I could Google this. I'm not going to. I'm going to use a math table book. Okay, because I'm going to show you how to use this just to show you that these things do legitimately exist. I didn't even look it up beforehand. Okay, so I could have bookmarked it. So let's just see how you use these ancient things. Okay, integral table. So it's elementary integrals. This one is a plus bx. In this, my integration variable is x. So my x in my equation is really just a constant a. So that's that. No. I'm looking for a squared plus x squared to the 3/2 on the bottom. Okay, so I'm getting... I'm starting to see stuff I like. A plus bx, no. Watch me not be able to find this, and then I'll feel dumb. Okay, look, right there. Is that it? X squared plus a squared cubed to the square root. I think that's it. I'm just trying to think. So in here I have dx and dy. My a is, I have the plus, and then I have a squared is x squared, and x squared is y squared to the 3/2. Yeah, so if I take this, yeah, I think that's the same thing. Okay, so let's write that down. So this is going to be equal to I x mu naught over 4 pi. Okay, so now I have, looking at I have x, which is going to be my y, over a squared, which is going to be, a squared is x squared. A squared is, right, x squared. And then I have the square root of x squared, which would be y squared plus x squared. All that. I think that's right. If it's not right, I don't know what I'm going to do. From negative L over 2 to L over 2. Oh, there was a negative sign there. Okay, so now I get one of these x's is going to, one of these x's is going to cancel because I don't have, that's a constant. I don't have to evaluate that. And x squared plus y squared is no, I can't do that. Okay, so let's just factor that out, and I get bz equals negative I mu naught over 4 pi, and then I have 1 over x, and then I have this, it's going to be at, I'll just put in L over 2 over, I've already factored that out, and then I have L over 2 squared, the square root of L over 2 squared plus x squared minus negative L over 2 over the square root of, again, the same thing, L over 2 squared, that's parentheses, plus x squared. Okay, so this is good because when I square that, the negative goes away. So these have the same common denominator, and I have 2 of these. So I get, this is equal to negative I mu naught over 4 pi 1 over x L over the square root, I'll just put it backwards as x squared plus L over 2 quantity squared. And that's right. I did it. So the equation I have is I use r instead of x, but that's the same thing because then I can just call that r. Okay, now if I let x be very small, if x, so let's rewrite this because that's kind of messy. And the negative sign doesn't really mean anything because it's, I found the scalar value anyway. Okay, so I can't believe I made it. You know, sometimes you just get surprised yourself. I'll be honest. So I have bz, I'm going to change it to r, equals, and this is the magnitude. So it's mu naught over 4 pi. And then I have li over r, the square root of r squared plus L over 2 quantity squared. Now, if r is much less than L, then on the bottom down here, this term is going to be very, very, very large compared to that. So I can just say this is going to be the square root of L squared over 2, which is this L over 2. So I get approximately equal to mu naught over 4 pi, and then I have Li over r, and then this just becomes L squared over 2, or L over 2. And so that L's cancel, and the 2 goes up top, and I have mu naught over 4 pi 2I over r. That's right. And so one of the things people say, oh, well, the 2 can cancel with the 4. True. But don't do that because this is exactly equal to 10 to the negative 7th, and then it just makes it a little bit more awkward if you do cancel. Okay. So we did that. Now on to part 2. So what we're going to do in part 2, in Python, I'm going to do the exact same thing. So the first thing I'm going to do is take an actual wire. I'm going to make this as a whole bunch of spheres. I'm going to do this the easiest way. So these are actually spheres. So each one, so I'm going to break this into n pieces, and this has a length L. So this, if that's n pieces, then the length of each piece, dl, magnitude, is going to be the total length divided by the number of pieces. And then I'm going to make this as simple as possible, so there's going to be some approximations. This piece, I'll just start down here. I'm going to let n be really large. Okay, so if that's the case, I guess I won't. So this first location right here is going to be equal to, this is going to be negative L over 2, but then I have to go up a little bit. I have to go up dl over 2, right, to be in the center of that. And that's where I'm going to put my first sphere. And then I can put my next sphere a distance of dl up. And I can just keep adding up all my spheres like that. And that's the first thing I'm going to do. After that, I'll have my observation location. I'll call that OBS. And then I can calculate this vector from there to there. And then I can use dB equals mu naught over 4 pi I dl cross r over the magnitude of r cubed. And then I just add up all the magnetic fields into all the pieces, and I should be done. Then after that, I think what I'll do, I'll stop there. I'm not going to do it as a function because it'll just be, well, we'll see. Let's see how it goes. Okay, let's switch over to Python, and let's just see how things go. I'm starting from scratch here, okay? So if you're not too familiar with Python, maybe I can give you some links down below. No, that's not what I want. Computer view. There we are. Okay. Here we are. Let me make that one a little bit bigger. I'll leave the camera on for now just so that it makes everyone happy. Okay, so the first thing I'm going to do is just put that constant. I'm going to call it mu equals 1 times 10 to the negative 7th. It's really mu naught over 4 pi. I should call it something else. Let's call it km for k, the mu constant. I don't know. Okay, now I need to say L equals, what is it, 0.5, I equals 1. I said that before. Now I'm going to actually make my spheres. Let's just say n equals 10. And I need to know the location, the observation location. So let's put that as a, let's just say R OBS equals vector 0, 0.05, no, 0.05, 0, 0. That's 5 centimeters, right? Okay, so that's what that is. So I'm centering this on the origin. Where is that first location going to be? Let's draw that first sphere. I'll call this R start equals vector 0, negative L over 2, plus, let's put dl equals L divided by n. So this will be plus dl over 2, 0. So that's that starting location. That's where I want to put my first sphere. Now let's make the sphere. So I'm going to say this. And I'm going to do this. This isn't the best way to do it. This is the way that I think people find makes the most sense to them. So I'm going to have a counter called n0. And I'm going to say while n, lowercase n is less than n, then do the following. And this make a sphere. Okay. So the first sphere is, I'm just going to draw it. Sphere position equals r. Yeah. Watch this. R start plus n times dl. Okay, let's do this. Plus dl over 2, and let's say the dl is the vector 0. Yeah, so if right here what I did was I turned dl into a vector. And then that way, when I add dl over 2 in there, it gives me the same thing. But now down here, I can take that starting location and add a scalar value times dl. So when n is equal to 0, it's going to be at r start. And the next one, n is equal to 1, it's going to be dl up. And that should work. Okay, and then we need to give it a radius, or it will put it at 1 meter. So radius is going to be equal to, let's say, if it's 50 centimeters long, let's put a centimeter. And then I'm going to increase the value of n. N equals n plus 1. I'm going to save this because when bad stuff happens, you always want to save. Numerical B magnetic field due to wire. It's kind of long. Okay. Let's run this thing and see what happens. Okay. Let's do this. Let's just print. Oh, yeah, let's see. I didn't give it an actual name, so let's just print this thing right here just to check and run it. So the last, if my wire is 50 centimeters long, the last piece, it would be at 0.225 0.25. That, and then I add in half of that. Skip. 0.25. Yeah. Yeah. Okay, so that seems like it's working. Now we can do the thing that we want to do, which is put more than 10. Once you get it working I like 10 because you can usually see them and count them. You could count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yay! And now we can change it to 100. Okay, now it actually looks like a wire. And this is in 3 dimensions, so you can rotate it around. Okay, I have my observation location. I have that. I have my sphere. Let's actually call this R wire, RW, equals this. It's the location of that. That way I don't have to, I can refer to that. And then I can just say RW. Let's just run it to make sure I didn't break anything. Okay, that still works. Now I can calculate R, the vector. It's going to be the vector from. Let's go ahead and put our observation as a sphere. POS equals vector. That's where that's at. The radius, let's put it as 0.021, and let's make it yellow. Color equals color.yellow, and let's run that. Yeah, there it is. Okay, that's fine. Kind of closer than I expected, but that's fine. So now I'm going to say R is the vector from the wire to the observation location. So that would be ROBS.POS minus RW. Remember, RW is just a vector. So that is my R value. Now up here, I'm going to add in B equals 0. And then down here, I'm going to say dB. I'm just going to type in that equation that I had before. So it's my constant, Km, times I times the cross product, cross is built in, of, let's say, dl and r, divided by the magnitude of r cubed. So cross is a built-in function in Python that returns a cross product, yay. Magnitude is a built-in function that returns the magnitude of a vector, double yay. Now I can take, that's the magnetic field due to those little pieces. Now I can take that and add that to my existing. So I'm going to take that piece, add it to whatever I started with, and I'm going to keep adding it up as I move along, and that should be it. And then I can say print B equals B. Tesla. Let's see if this works. No. Something happened. Cannot add a scalar and a vector. Where am I adding a scalar and a vector? R start times NDL I cross. It says you can't add. Cannot add a scalar and a vector. Oh. B, aha. Vector. This is the things that I get on my students, right? There is a difference between the number 0 and the vector 0. And I can't add vectors to that because I said it was 0 scalar. Okay. I did that on purpose. So there's my magnetic field in this negative z direction, just like I said. Now let's calculate the theoretical value. So let's say B theory 1, and that's going to be the longer version. I'm looking at my notes over here. So it's going to be mu naught, which is Km, times L times I divided by, I guess that'd be X, right? Divided by X times the square root of X squared. I'm just making sure these are all scalars, yes. I know I never said what X was. So let's go up here and say X equals 0.05, and then put this at X. Just to be all fair. Okay, so X squared plus L over 2 squared. No, L. L over 2 squared. I think that's it. Okay, let's print that. Print B theory 1, and there will be another one, equals B theory 1 Tesla. And that's this Z component. I should save this. And run it. Uh-huh. I mean, it's always surprising when things work. And that you can't get anything working better than that. Let's just try this. What if I only had 10 points instead of 100? Okay, so, wow. That still works very well. Now, what I've found in the past is that when I can get weird values, because if this is too close to one of the data points, one of the pieces. Okay, and let's do the other version, B theory 2. B theory 2 is going to be Km times 2 times I divided by R, but in this case R was X. Is that what I had? Yeah, X. And let's say I'm going to print B theory 2 equals, and this is if it's a long wire theory. So B theory 2 Tesla. Okay, so it's fairly close, right? I get 3.9 versus 4. So these two numbers don't even agree. These two are the two theoretical weights. They don't quite agree, but it's close. Okay, now ready for the magic. Oh, you thought I was done. Oh no, I'm not done. What if I do this? What if I change my observation location to let's say L over 2. So now instead of finding the magnetic field right there, I'm going to find the magnetic field up here. Okay, I'm going to run that. It's still in the Z direction. Okay, but it's different because now these are much further away. I'm doing a different integral, right? I'm not doing that simple integral I did before. I think you could still do this just by changing the limits of integration, and you should be able to get the same thing. But I didn't do that. But I can put this wherever I want. I can put this observation location wherever I want because I didn't make any approximations for directions or anything like that. This is legitimately the magnetic field. I can even put it, way up here on the x-axis. And that's what's nice about this. Okay, let's do one more thing. Let's do this. I'm going to say B scale equals 1 to the 5th. And then I'm going to say B arrow equals arrow. Position is equal to obs.pos. Axis is going to equal B times B scale. And let's make it cyan. Color equals color dot cyan. See what happens. Maybe that's too small. Or did it give me an error? It didn't. Can't OBS. What are OBS? That's why. And there you go. That's the direction of the magnetic field at that location. And I can put it wherever I want. Let's put this at x, 2 times x. I don't know, I'm just making up stuff. And there's a magnetic field. So you can draw that as a vector. And so that B scale down here, the B scale is because the magnetic field value is 10 to the negative 6th. So if I just plot the arrow length as 10 to the negative 6th, that's how many meters long it'd be, and you couldn't see it. So I have to multiply it by scale in order to get it up to reasonable sizes, but I think that's enough. Okay, so I'm going to give you this code for homework. For homework, what would be cool is to take this and plot the magnetic field value, the Z component of the magnetic field as a function of distance. So run this at different distances and plot that and compare that to the theoretical value and show that it is 1 over r. So that'll be a homework assignment for you. That's it.